So, music is a very emotional art form, and it's something that is very uniquely human, and there's a lot of artistic expression in it. But what most people don't know is that there exists a mathematical basis in music and why certain notes sound good together and what the relationship between these notes are. So, there exists a very interesting connection between math and music, and this was originally discovered by Pythagoras, who discovered that when you divide the vibrating length of a string in half, you get a note that works very well with the original note when played together. Now, this concept stems from the frequency of the notes. So, what a frequency is, or what a sound is rather, is when a note is played, there are going to be alternating pockets of high and low frequencies. And these are sort of viewed like pulsations in the air that hit your ear. So what a frequency is how many pulsations there are in the air per second. So let's say you have a note that's 440 hertz. That means that there are 440 pulsations per each second. Now, when you take this, let's say you take a note and you're going to double the frequency of it. So we have 440 hertz. Let's introduce another note that's 880 hertz. What this means is the frequency is going to be twice as much in a given second, or there are going to be twice as many pulsations in the air per each second. Now, since these frequencies are caused by alternating pockets of high and low pressures in the air, there are peaks and valleys in the pressures. So for each second, when you play the original note and the new note together, every other peak of pulsation of this new note at 880 hertz will line up with every peak of pulsation of the original note at 440 hertz. And this is the concept known as the octave. Now, another type of note that works good with the original note is the fifth. When you play the fifth and the original note together, every third peak of pulsation of the fifth lines up with every other peak of pulsation of the original note. This creates a ratio of 3/2, or 1/2. And the third part of a chord, because a chord is consisting of three notes: an original note, the root note, a fifth, and a major third. When you play all three of these notes simultaneously, every fifth peak of pulsation of the major third will line up with every fourth peak of pulsation of the fifth, which will in turn line up with every third peak of pulsation of the original note. And this lining up of the notes happens every 0.015 seconds. The frequency of these notes in Western music is based upon 12 steps between and including the octave. So a good question arises in what will cause these different notes, like where should we space these notes and how should we space these notes. So taking the 12th root of 2, you get a number 1.0595. And what that means is 1.0595, that multiplied by itself 12 times will result in 2, or double the frequency of the original note. Now, when you take this number 1.0595 and you raise it to the 7th power, what you end up getting is a number very close to 1.5, which is actually the ratio of the 5th note to the original note. And then if you take 1.0595 and you raise it to the 4th power, you get a number 5/4, which again is similar to the ratio of the major third note to the original note.
Mathematics plays an important role in the analysis of music, especially when it comes to tuning an instrument to making certain chords sound a particular way. Figuring out how to line up certain pitches mathematically helps musicians create music that sounds good together and works in unison. Professor Anil Venkatesh introduces us to the 19th century physicist Hermann von Helmholtz, whose idea was when you played two different notes at the same time, they both emit different frequencies which ultimately overlap, creating one sound that sounds good. His theory claimed that when these emitted frequencies are lined up, they create a consonant chord, and if not lined up correctly, they create roughness and turbulence. The frequencies radiating from strings line up to generate chords that are pleasing to the ears. To find chords that sound good together, we have to find an interval between the notes that make the frequencies line up. This idea encourages musicians to find inputs that create the least amount of dissonance and rather make music that creates harmony and sounds well when put together. This idea is called linear programming, which is an algorithm that uses linear objectives to find a place in the function closest to the y-axis. The x value found from this determines a new half step which is used in order to tune the instrument with the least amount of discordance. Professor Anil Venkatesh introduced us to George Sikor, a musical arranger who discovered an x value, 18/5 to the 1/19th power, which ideally generates a consonant chord. However, this only worked on small instruments. This didn't apply to larger instruments. But by using his idea of linear programming, musicians are able to find different x values which are able to work for larger instruments and create chords that do sound good together.
So Sarah made a point about tuning, and when you tune an instrument, you're tuning the strings of an instrument. And the strings of the instrument are what make the sound. So speaking to Provost Everett, we were able to understand timbre as a big part of the connection in math and music. Timbre is known as the color of the musical tone, or rather, the tone quality. It's rarely discussed in music classes, although it's a critical part of what we hear when we're listening to music. Every culture has different timbres, and it pertains to the qualities such as the roughness, the vibrato, and the loudness. In all aspects of playing music, whether it's bow speed, bow pressure, vibrato, or portamento, which is sliding between the notes, we are able to distinguish the musicians themselves. These special qualities can all be measured in numbers. These structures can play for a certain length of time depending on the tempo. For example, if a quarter note is 120 beats, there would be 2 notes per second. We can also turn data into sound, also known as sonification. We take the parameters in streams of numbers and map them as variables in sound such as amplitude, frequency, and rhythm. We then listen and try to find patterns within the music. For example, we can connect protein sequences to music. Protein sequences allow us to map sound as well. When we take the chaotic protein sequences and put notes in place, we are able to hear the variation in the music. By this, we're able to understand the patterns.
Speaking of patterns, David Cope is a well-known composer who tackled patterns between music and math, specifically discussing how one could use computer algorithms to create music, perhaps in a more efficient way than traditionally made music. He proposes that all new music takes inspiration from already extant musical compositions, since all melodies are derived from the same group of musical notes, much like how all English sentences are derived from the same alphabet. With this information, Cope theorized that a computer program could be created that contained a database of all pre-existing music. Through this database, an algorithm could determine a completely new melody, potentially with more accuracy than one could determine sans technology. Based off this hypothesis, Cope created a computer program called Experiments in Musical Intelligence, which would break down the compositions of a specific musician and, using computational algorithms, create a completely new composition similar to what the musician would create. Furthermore, this program was not only limited to one musician, but would create new compositions for any composer whose music was input into the database. One composer that Cope experimented with in 1993 was Bach, and this experiment was a success. This work culminated in Cope's album, Bach by Design. Cope's work has proven to be controversial, but one thing's for certain. His work has definitely advanced the study of mathematical music and musical programming.